Okay, some solved problems for chapter 35. I have two small sound sources that are located some distance apart, and they're sending out some wavelength. And we're going to say these guys are coherent, so you can kind of imagine this guy sending out some waves, and this guy sending out waves. It's going to go in circles, and there's going to be regions where they constructively interfere, and so we're going to have large crests, and there's going to be regions where they constructively or destructively interfere, so there's going to be essentially no motion. And I've kind of already written the equations. This is going to be the equation we use for part A. This is going to be the equation we use for part B. Essentially, this person's going to kind of walk around in a circle, always staying 1.5 meters away, and figure out what these x are, keeping x less than 1.5 meters. So for part A, we're going to say x minus 1.5 meters is going to be equal to m multiplied by 0.34. So x is going to be equal to 1.5 plus m multiplied by 0.34. And we can kind of see, because I want x to be less than 1.5 meters, I'm going to be using the negative m's. And what I'm going to do is I'm just going to pop open this little table and say just evaluate x for all these various m values. And so I'm going to get 1.5 meters, and then I'm going to get 1.16 meters, 0.82 meters, 48 or 0.48 meters, and 0.14 meters. So those are kind of my solutions. We do the same thing for part B, only we're going to say x minus 1.5 is going to be equal to m plus 1/2 multiplied by 0.34. So x is going to be equal to 1.5 plus m plus 1/2 multiplied by 0.34. Cut to the magic table. They're just going to evaluate x for these various values of m, and I'm going to get 1.33 meters. I'm going to get 0.99 meters, 0.65 meters, and 0.31 meters. Okay, I have some red laser light. I know the wavelength, and I'm going to illuminate a screen that's 1.8 meters away. So the nomenclature of this chapter, that's capital R. And I know that there's some the separation between the dark bands, some delta y, that's going to be 4.2 millimeters. Now I know these dark bands are going to occur for m is equal to 0 plus or minus 1, 2, 3, 4 at this y right there. Really what I'm looking at, what I'm given is a distance between the dark bands, so I can pick any two dark bands I want. Let's just pick m is equal to 0 and say r multiplied by 1/2 lambda divided by 2, so that's y0. We'll pick y1, and that's going to be r multiplied by 3/2 lambda divided by d. So delta y is going to be y0 minus y1, which is simply going to give me r lambda divided by d. And now I know everything, or now I have an equation where I know that, and I know that, and so I can solve for d. So d is going to be equal to r lambda divided by that separation distance. Now it's a simple matter of plug it in. R is 1.8 meters, lambda is going to be 450 times 10 to the minus 9th meters, and delta y is going to be 4.2 millimeters, 10 to the minus 3. And at the end of the day, I get my slit width, or slit separation, to be equal to 1.93 times 10 to the minus 4th meters. And lastly, we want to have a non-reflective coating to view some artwork. As you can see, I'm highlighting my own artwork. So what we're going to do is we're going to take this glass and we're going to put a coating of titanium dioxide on there. And essentially what we want to do is we want to have this green light, given the wavelength, and have some green light incident right here. It's going to be reflected. It's going to interfere with the light that's reflected off of that surface. And the question is where are there phase shifts and where are there not? It depends on the index of refraction of these three guys right here. So here we have a fast to slow, so there's not going to be a phase shift. Here we have a slow to fast, so there is going to be a phase shift. So we want destructive interference when there is a 180 degrees phase shift, and that's given by 2t is equal to m lambda. Have to be kind of careful here. Remember, this is going to be the lambda in the material, so the lambda in the TiO2, so that's going to be equal to lambda divided by the index of refraction of that material. So we can solve for the thickness. The thickness is going to be equal to m divided by 2, with this lambda being the lambda in the material, so lambda divided by index of refraction of titanium dioxide. And we're going to say that this is going to be equal to, I'm just going to leave m as a constant for a little bit, and then we're going to have 505 nanometers. Got my 2, and I got my index of refraction, which is going to be 2.62, and so that's going to be essentially 96.4 nanometers multiplied by m, where first for part A I'm going to say m is equal to 1, so the thickness is just going to be equal to 96.4 nanometers, so that's part A. Now part B, it says, well, if it's too thin to stand up to wear, what other thicknesses would also work? And cue the fancy table, and I'll get part B kind of in there, where I evaluate this expression right here for m is equal to 2, 3, and 4. So when m is equal to 2, the thickness is going to be 192 nanometers. And then when m is equal to 3, it's going to be 289 nanometers. And when m is equal to 4, it's going to be 386 nanometers. And on to solve problems for chapter 36. So we'll start off with number 5. It says blah blah blah, sound waves can diffract too. The only thing that's going to be different is going to be the wavelength. So here I've gone ahead and I've written us down the wavelength, the slit width, and the distance between the source and the screen, if you will. And in this case, the screen is going to be a microphone that's kind of going to start off at the center and work our way up, and it says at what distances is the intensity detected going to be 0. This is kind of like saying, hey, you know, where are the dark spots? So we're going to say, well, we're going to have the dark spots destructive interference at sine theta is equal to m lambda divided by a. So hey, we can figure out what theta is. Theta is simply going to be the arc sine of m lambda divided by a. And if I know what theta is, I can use trig to figure out what y is. So theta is simply going to be equal to the arc sine. In this case, it's the very first one, so m is going to be equal to 1. I know my wavelength is going to be 0.09 meters. Divide that by 0.12, and I get my angle to be equal to 48.6 degrees. Now just a little bit of trig, we can see that y is going to be equal to x multiplied by tangent theta. So it's simply going to be equal to 8 meters multiplied by tangent of 48.6, and this distance is going to be plus or minus 9.07 meters. And the very last problem involves a diffraction grating. You know, we're going to be having bright spots, and we really only have one equation for diffraction grating, so I've taken the liberty of writing it. I'm going to say we're going to shine some red light on there, so we've got some red wavelength. We're going to get some angle associated with the third order bright spots that says m is going to be equal to 3. Now we take that same diffraction grating and we shine it with some violet light, wavelength of 400 nanometers. What's the angle of the second order bright spot? So m is equal to 2, and the angle is equal to what? So really, the only thing that's going to be constant in this equation right there is going to be d. So we could actually just say m times lambda divided by sine of theta is going to be equal to d, which is going to be constant. And so we could say if this is red light, red light, red light, it's going to be the same as saying violet light, lambda violet light, and then sine theta for violet light. Now it's a simple matter of isolating that guy right there, so we're going to say sine theta of violet light is going to be equal to sine theta of red light multiplied by m of violet divided by m of red, and then lambda violet over lambda red. And now it's a simple matter of plugging these guys in. Sine of 65 degrees, and this is going to be the second order bright spot divided by the third order bright spot, and then we're going to have 400 nanometers divided by 700 nanometers. And we can just take the arc side of that. I'm going to spare writing arc sine and just cut straight to the chase. Theta for violet is going to be equal to 20.2 degrees.